Welcome to the Deep Dive, where we try to unravel the mysteries shaping our amazing planet. Just, pause for a moment and picture the world around you, maybe the rugged peaks of a mountain range, or those intricate arches carved into deserts, or even just the rich, dark soil in your garden. These features seem so permanent, don't they?
They really do. But they're constantly changing, and that's what we're digging into today.
Exactly. What are the unseen forces tirelessly at work, patiently transforming solid rock into something completely new?
It's a great question. And this deep dive is all about two fundamental processes. Weathering, that's the slow, relentless breakdown of rock and its incredibly vital product, soil.
Yeah.
Understanding these as well, it's like getting a backstage pass to Earth's dynamic geology.
Yeah, it connects the huge scale of landscapes right down to the ground we walk on, the food we eat.
Precisely. It links the grand scale to our everyday lives.
Right. So our mission today is to unpack how rock crumbles, why some bits last ages while others vanish, what makes soil so crucial for life, and importantly, how our own actions impact this really delicate ancient system. Get ready to see the world a bit differently, maybe spotting the signs of Earth sculpture everywhere.
Okay.
So let's start at the beginning, this invisible architect. What is weathering exactly?
Well, simply put, it's the physical breakdown and the chemical alteration of rock. It happens right there at the Earth's surface, where rock meets the atmosphere, water, life.
It feels incredibly slow, almost like nothing's happening.
It is slow, imperceptible sometimes, but its power over geological time is just immense. And it's really vital to see it as two distinct, though interconnected types. First up is mechanical weathering.
Okay. Now,
This is purely physical. Think of taking a big boulder and just smashing it into smaller pieces without changing what it's actually made of.
so no chemical change,
Uh,
just smaller bits.
Exactly. It's still the same rock mineralogically, just in fragments. And the key thing here, the really important part, is that this process vastly increases the rock's surface area,
Right. More surface exposed.
which makes it far more vulnerable to the second type, which is chemical weathering.
Okay, the chemical side.
Yeah, this is where the rock's internal composition is fundamentally changed. It's not just breaking it into pieces. Chemical weathering transforms the minerals within the rock into entirely new compounds, often compounds that are more stable at the surface conditions.
So it's like cooking. The ingredients actually change into something new.
That's a pretty good analogy, yeah. It happens because rocks formed deep underground, under intense heat and pressure, they find themselves in a very different, almost hostile environment when they get exposed at the surface. They basically have to adapt chemically.
And you said these two types are interconnected.
Oh, absolutely. They rarely work in isolation. Mechanical weathering creates those smaller pieces that increase surface area. It almost prepares the rock, you could say,
Right, sets it up.
making it much easier for chemical weathering to then get in and do its work. They're a powerful tag team, really.
Okay, that makes sense.
Yeah.
So let's explore those physical forces then, the mechanical weathering. You mentioned the big idea is increasing surface area.
Exactly. Think about dissolving sugar. Granulated sugar dissolves much faster than a solid cube, right?
Instantly almost.
It's the same principle.
Yeah.
More surface area means more places for chemical reactions or even further physical breakdown to happen. And there are four main physical forces doing this. First, probably the most famous, is frost wedging.
Frost wedging, that sounds cold.
It is. It relies on water's really unique property.
Okay.
It expands by about 9% when it freezes. Like if you forget a glass bottle in the freezer.
Oh yeah, I've done that. Messy.
Exactly. So in nature, water seeps into tiny cracks in rock. When it freezes, it expands and acts like a wedge, literally prying the rock apart bit by bit.
Over and over.
Over countless freeze-thaw cycles, yeah. This can break off huge angular chunks of rock, creating those piles of debris you see at the base of cliffs. We call them talus slopes. And newer research even suggests ice lenses can grow within cracks, drawing in more water and exerting continuous pressure. It's pretty effective.
Wow. So it's this constant tiny battle. What else physically breaks rocks apart?
Well, another significant one is salt crystal growth. This is really common in dry regions or along coastlines.
Salt, like from the sea.
Yeah, or even salty groundwater. The salty water gets into rock pores and cracks. Then, as the water evaporates, the salt that's left behind starts to form crystals. And these growing crystals exert pressure.
Pushing the rock grains apart.
Exactly, pushing grains apart or widening existing cracks. If you've seen how road salt makes pavement crumble in the winter, that's basically the same process in action.
I definitely have seen that. Okay, what's next? There was something about unloading.
Yes, sheeting, or sometimes called unloading. This happens with large masses of igneous rock, especially granite, that formed deep underground when erosion gradually removes the overlying rock.
The pressure comes off.
Precisely. The immense confining pressure is reduced, and the rock mass expands slightly upwards. This expansion causes these large concentric slabs, almost like layers of an onion, to break loose and peel away.
Wow. Are there famous examples of this?
Oh yeah, Stone Mountain in Georgia is a classic. Half Dome and Liberty Cap in Yosemite National Park too. They're really spectacular examples of these exfoliation domes, as they're called. It shows just how much pressure rocks are under deep down.
Incredible. Nature's sculptors at work. And don't living things also play a part?
They absolutely do. That's biological activity. Plant roots are amazing engineers. They grow into existing cracks.
And just wedge them further apart.
Yep, that's root wedging. Burrowing animals are important too. They move fresh rock material up to the surface where it weathers faster. Even decaying organisms produce acids that contribute to the chemical side of things. And, well, we humans make a difference too, with blasting for mining or road construction.
Right. And you mentioned joints earlier, natural fractures.
Yes, joints are crucial. These pre-existing fractures create patterns in rock outcrops and act like highways for water to get deep into the rock, speeding up all these weathering processes significantly.
Okay, so the big picture for mechanical weathering is physical forces like ice, salt, pressure release, even life, constantly chip away at rock, creating more surface area, and really setting the stage for deeper chemical changes.
Exactly. Which brings us neatly to chemical weathering, Earth's sort of slow cooker process.
Right, transforming the rock itself.
Yes. And remember, it's highly interconnected with mechanical weathering. The physical breakdown makes more surface area available, and the chemical changes weaken the rock, making it easier to break physically. It's all about transforming unstable minerals into new, stable compounds that fit the surface environment.
And water is the key player here, you said.
Water is the absolute superstar, yeah. Pure water itself is a decent solvent, but when it dissolves even tiny amounts of acids, its power to corrode rock increases dramatically.
Okay, acid rain.
Acid rain is a factor, especially human-caused acid rain, but even natural rainwater is slightly acidic because it dissolves carbon dioxide from the atmosphere, forming weak carbonic acid.
Okay, so what are the main chemical processes?
Well, we usually talk about three main ones involving water. First is dissolution. Some minerals simply dissolve in water or slightly acidic water. Think of halite, common table salt. Water molecules literally pull the sodium and chloride ions apart.
Easy enough.
But here's the thing. Most common rock-forming minerals don't dissolve easily in pure water, but add that weak carbonic acid. And suddenly, minerals like calcite, which makes up limestone and marble, dissolve quite readily.
Ah, and that's how caves form.
Exactly. That's how spectacular limestone caverns like Carlsbad Caverns are formed over long periods. The downside, of course, is that this same process deteriorates limestone and marble buildings and monuments, especially where acid rain is a problem.
A direct link between geology and preserving our history. Okay, what's the second chemical process?
Second is oxidation. Most people recognize this as rusting.
Like iron rusting.
Precisely. It's when an element loses electrons, often by combining with oxygen. Iron is common in many dark silicate minerals, like olivine or pyroxene. When they weather, the iron oxidizes, combining with oxygen to form reddish-brown hematite or yellowish limonite.
So that's where the rusty colors on rocks come from.
That's often it, yeah. Those iron oxides give many weathered igneous rocks that characteristic rusty coating, and they act as pigments in many sedimentary rocks. Think of the reds and oranges in the Grand Canyon.
Okay.
But there's an environmental downside here, too. When pyrite, an iron sulfide mineral often found with coal, oxidizes, it doesn't just rust, it produces sulfuric acid. This leads to acid mine drainage, which is highly toxic to streams and aquatic life.
That sounds really serious.
Okay, and the third major one is hydrolysis. This is basically the reaction of any substance with water. It's super important for weathering silicates, which are the most abundant minerals in Earth's crust.
How does that work?
Essentially, hydrogen ions from water, or often from water-containing acid, attack and replace positive ions, like potassium or sodium, within the mineral's crystal structure. This disrupts the structure and breaks the mineral down.
Can you give an example?
Sure. Take potassium feldspar, a really common mineral in granite. It reacts with carbonic acid and water. The hydrolysis breaks it down into kaolinite, which is a type of clay mineral, plus some soluble salt and silica, which get carried away by water.
And clay is important. Okay.
Very important. Clay minerals like kaolinite are very stable end products of weathering. They make up a huge chunk of the inorganic material in soils and are the main component of shale, the most common sedimentary rock.
Okay, I see. And all these chemical processes working together can lead to that distinctive rounded shape we sometimes see in boulders.
Yes, that's spheroidal weathering. Chemical weathering attacks edges and corners of an angular rock block more effectively than the flat faces, simply because there's more surface area on the corners and edges.
Right, attacking from multiple sides.
Exactly. So those corners and edges weather faster, gradually rounding the block into a sphere. You see beautiful examples in places like Joshua Tree National Park.
Fascinating. So, chemical weathering is basically earth recycling minerals, breaking down the unstable ones formed deep inside and creating new, stable materials like clays, which become building blocks for soil and new rocks. It's a continuous transformation.
You got it. And what's really interesting is that not all rocks weather at the same pace. This differential weathering is actually what carves out many of our most dramatic landscapes.
Differential weathering, meaning some rocks resist more than others.
Exactly. The more resistant rock layers stand out as cliffs or ridges, while the weaker layers erode away faster, forming slopes or valleys.
So what makes one rock tougher than another? What controls the weathering rate?
Two main things control it. First are the rock characteristics themselves.
Like what it's made of.
Yes, mineral composition and solubility are key. Think about an old cemetery again. Granite headstones made of hard silicate minerals last for ages. Marble ones made of calcite.
Dissolve much faster.
Right. Exactly. It ties back to mineral stability. Minerals like olivine, which form first at high temperatures deep down, are less stable at the surface compared to quartz, which forms last and is very resistant. Also, physical features like those joints, the fractures,
They let water in deeper, speeding things up.
greatly speeding things up, yes. The second major factor is climate.
Ah, climate. Makes sense.
It's huge. Temperature and precipitation are crucial. We already talked about freeze-thaw cycles driving frost wedging, but for chemical weathering, the optimal conditions are warm temperatures and plenty of moisture.
So tropical climates weather rocks fastest chemically.
Generally, yes. Chemical weathering is pretty slow in polar regions because the water's locked up as ice, and it's also slow in very dry, arid regions because there isn't enough water.
And vegetation plays a role too.
Definitely. Lush vegetation means more organic matter, which decays to produce organic acids in the soil, boosting chemical weathering. And unfortunately, we have to mention human impact again. Acid rain, caused by burning fossil fuels, releases sulfur and nitrogen oxides that form acids in the atmosphere, significantly accelerating chemical weathering globally.
Okay, so rock type and climate are the big controls. Let's shift focus now. We've broken down the rock.
Mhm.
What about the result? Earth's living skin, soil. We mentioned regolith, that loose layer of rock fragments. But soil is more than just broken rock, right?
Oh, much more. Soil is the specific combination of that mineral matter from weathering, plus organic matter, water, and air. Critically, it's the portion of the regolith that can actually support plant growth.
So it's alive, in a way.
You could say that. It's often called the bridge between life and the inanimate world. Think about it. All the essential elements plants need, derived from Earth's crust through weathering, are made available to them through the soil. And ultimately, that supports us.
That really puts its importance in perspective. And it's not just sitting there, is it? You called it an interface.
Yes, it's a fundamental interface in the Earth system. It's where the solid Earth, geosphere, the air, atmosphere, water, hydrosphere, and life, biosphere, all meet and interact dynamically. It's incredibly sensitive to environmental changes.
So what's actually in soil?
If you could separate it out, roughly half its volume is solid material, a mix of mineral matter and humus. Humus is that dark, decayed organic stuff from plants and animals. The other half is pore space, filled with varying amounts of air and water.
And humus is important.
Absolutely vital. It's a major source of plant nutrients, and it dramatically improves the soil's ability to hold water.
Okay. And I've heard about soil texture. Sand, silt, clay.
Right, soil texture refers to the proportions of different particle sizes. Sand, largest, silt, medium, and clay, smallest. This texture is super important because it determines how well water drains, how much air the soil holds, how easily roots can penetrate, basically how well plants can grow.
Is there an ideal mix?
Often, yes. A soil called loam, which has a good balance of sand, silt, and clay, is usually considered ideal for many types of agriculture because it offers the best of all worlds, Good drainage, good aeration, good water retention, good nutrient supply.
And structure, that's different from texture.
Yeah, soil structure is about how those individual sand, silt, and clay particles clump together to form larger aggregates, which we call PEDs. Good structure creates larger pores, improving water infiltration and aeration, making it easier to cultivate and reducing erosion risk.
Okay, so soil is complex stuff. What's the actual recipe then? What controls how a particular soil develops?
It really comes down to a complex interplay of five key factors. First is the parent material.
The rock it started from.
Exactly. The source rock, or the unconsolidated sediment the soil forms on. If it forms right on top of the bedrock it came from, we call it a residual soil. If it forms on material that was transported maybe by a river, glacier, or wind, it's a transported soil. The parent material influences the initial minerals and the weathering rate, but over long time scales, the other factors often become more important.
Okay, factor number two.
Number two, and arguably the most influential overall, is climate.
We keep coming back to climate.
Because it's fundamental.
Yeah.
Temperature and precipitation determine the type of weathering, mechanical versus chemical, that dominates, how fast it happens, and how deep it goes. Climate controls leaching, the washing out of minerals, and strongly influences the types of plants and animals that live there, which also affects the soil.
Right, which brings us to factor three, plants and animals.
Indispensable. They provide the organic matter, the humus. Microorganisms like bacteria and fungi are the workhorses, decomposing organic matter, creating organic acids, and crucially, converting nitrogen from the air into a form plants can use.
And bigger creatures too, earthworms.
Earthworms are fantastic. They mix the soil, create channels for air and water. They're soil engineers.
Okay, parent material, climate, life.
Hmm.
What else?
Factor four is simply time. Soil formation is slow. The longer the processes have been operating, generally the thicker the soil becomes and the less it resembles the original parent material. It takes time for distinct layers or horizons to develop.
Makes sense. And the last one,
The fifth factor is topography, basically the shape or lay of the land.
how does the slope matter?
A lot. On steep slopes, runoff is fast, erosion is high, and water doesn't soak in well, so soils tend to be thin and poorly developed. In low-lying, flat areas like bottomlands, soils might be thick and dark, but often waterlogged because drainage is poor.
So where's the sweet spot?
Often, it's on flat to undulating upland surfaces. These areas tend to have good drainage, minimal erosion, and good water infiltration, allowing for thick, well-developed soils. Even the direction a slope faces matters. Think south-facing versus north-facing slopes getting different amounts of sun, which affects temperature, moisture, vegetation, and ultimately the soil itself.
Wow, so it really is the combined influence of all five, parent material, climate, organisms, time, and topography, that determines what kind of soil you find in any given place. It's not just dirt at all.
Not at all. Each soil tells a complex story. And to understand that story, we look at the soil profile.
The layers you mentioned.
Exactly. If you dig a pit, you see a vertical cross-section showing distinct layers called horizons. These develop as the soil-forming processes work their way down from the surface.
Can you walk us through a typical profile, say in a temperate, humid place?
Sure. Right at the top, you have the O horizon. That's mostly organic matter, loose leaves, twigs, partially decayed humus.
Okay, the surface litter.
Below that is the A horizon. This is mineral matter mixed with a good amount of humus, so it's usually dark. The O and A horizons together are what we commonly call topsoil, really crucial for agriculture.
Got it, topsoil.
Beneath the A, you often find an E horizon. It's typically lighter in color because this is a zone of alluviation and leaching. Water moving down washes out fine particles like clay and dissolves soluble minerals, carrying them deeper.
So stuff is being removed from the E horizon.
Yes, and it accumulates in the layer below, the B horizon, or subsoil. This is the zone of accumulation. Clays, iron oxides, other materials washed down from above tend to build up here. Sometimes so much clay can accumulate that it forms a dense, impermeable layer called a hardpan.
Okay, O, A, E, B.
Those four horizons together, O, A, E, and B, are collectively called the soilum. That's considered the true soil, where most of the biological activity happens.
And below the soil.
Below the B horizon is the C horizon. This is partially altered parent material. You can often still tell what the original rock or sediment was. It hasn't undergone the intense soil formation processes of the layers above. And below that, eventually, you hit unweathered parent material or bedrock.
That's a really clear picture of how soil develops in layers. With so many variations globally, How do scientists keep track? Is there a classification system?
Oh, absolutely. Given the sheer diversity, we need a system. It's called soil taxonomy. It's hierarchical, kind of like biological classification with broad categories called orders. There are 12 of them down to very specific series, thousands of those.
Are the names useful?
They try to be descriptive. For example, aridisols are soils of dry climates, arid, and septisols are young soils showing initial inception horizon development. It's a really important tool, especially for agriculture and land management, though maybe less so for, say, engineering site evaluations, which have different needs.
Right. Now let's bring humans back into the picture. You've emphasized soil is vital, but it forms incredibly slowly. That makes it essentially a non-renewable resource, doesn't it?
It absolutely does on human timescales, and sadly, it's one of our most abused resources.
How so? Can you give an example?
A really stark case study is the clearing of tropical rainforests. You see that incredibly lush vegetation and might assume the soil underneath must be fantastically fertile.
Yeah, you'd think so.
But it's often the opposite. The soils, often thick red-orange oxasols, are actually quite poor for farming. Here's the surprising thing. Most of the nutrients aren't in the soil. They're locked up in the trees and the rapidly cycling biomass. The heavy rainfall leaches nutrients out of the soil very quickly, and decomposition is so fast there's little humus buildup.
So when the forest is cleared,
The nutrient source is removed. The soil, now exposed, erodes rapidly because the tree roots aren't holding it and the canopy isn't protecting it from rain. And worse, when these iron-rich tropical soils are exposed to direct sun and bake, they can harden into a brick-like substance called laterite,
yeah,
making farming impossible within just a few years.
wow, that's devastating. A total misunderstanding of the ecosystem.
It highlights how crucial understanding soil science is, and this leads to the broader issue of soil erosion. It is a natural geological process, part of the rock cycle, but human activities, farming, logging, construction, have accelerated it enormously.
How does erosion typically happen, say, with water?
It often starts subtly. First, the impact of raindrops hitting bare soil acts like tiny explosions, splashing soil particles around. Then, water flowing as thin sheets across the surface causes sheet erosion. This sheet flow concentrates into tiny channels called rills, and if those aren't managed, they deepen and widen into gullies, which can carve up farmland catastrophically.
You had a statistic about river sediment.
Yeah, it's pretty staggering. Estimates suggest that before widespread human agriculture and land use changes, rivers carried maybe 9 billion metric tons of sediment to the oceans each year. Now, it's around 24 billion metric tons.
More than 2.5 times the natural rate.
That's the scale of our impact. And it's not just water. Wind erosion is a huge problem in drier areas, especially if protected vegetation is removed. The classic tragic example is the 1930s Dust Bowl in the American Great Plains. Natural grasslands were plowed up for farming, then drought hit, the soil dried out, and massive dust storms literally blew the topsoil away.
A devastating lesson. And this is still happening.
Yes, the urgent problem is that on over 1/3 of the world's croplands, topsoil is eroding faster than it's being formed. We are losing this vital, non-renewable resource at an alarming rate.
It sounds bleak. Is there anything we can do? Are there
Yeah.
solutions?
Thankfully, yes, there are many effective techniques for controlling soil erosion. On steep slopes, building terraces creates level steps that slow water runoff. Contour plowing, where you plow and plant crops parallel to the contours of the slope, acts like mini dams to trap water and soil.
What else?
Leaving crop residues, the stalks and stems left after harvest on the fields, provides cover. Planting strips of grass or cover crops between row crops helps slow runoff and filter sediment. Creating grassed waterways prevents gullies from forming in natural drainage paths. And in windy areas, planting windbreaks, rows of trees or shrubs, significantly reduces wind speed at ground level and protects fields.
So there are practical solutions available.
Absolutely. Implementing these soil conservation practices is crucial for sustainable agriculture and protecting this irreplaceable resource for the future.
Okay, so we've covered a lot of ground, literally. From the almost imperceptible crumbling of mountains by weathering, both mechanical and chemical, to the formation of that intricate, life-sustaining layer we call soil, shaped by parent material, climate, lifetime, and topography.
It's a journey from solid rock to living earth. We've seen how weathering sculpts landscapes and creates the raw materials, and how soil develops as a complex ecosystem at the interface of Earth systems.
And as you, our listeners, look at the world around you now, maybe take a moment. Think about how understanding these incredibly slow, profound geological processes, the cracking of a boulder by ice, the chemical transformation of feldspar into clay, the gradual layering of a soil profile. How does that change your perspective?
Does it deepen your appreciation for Earth's resilience? And maybe also for our shared responsibility? Because this soil, this product of millennia, is vital and non-renewable on our watch. We need to be stewards of it for future generations.
I certainly hope you'll look at landscapes, rocks, even the ground beneath your feet a little differently now, seeing the evidence of weathering and soil formation everywhere. Thank you for joining us on this deep dive.